This is chapter 3 on probability and random variables, the first part. And let's start. So this is a histogram of the data that we showed previously in the chapter 2, descriptive statistics. And what you see now is, okay, we could actually calculate the probability that Z would be between 20 and 30 by adding up the areas underneath the histogram. But what if I would ask you, okay, what's the probability that Z is larger than 45? Then we would be in trouble because we don't have that in the data set. Does that mean that the probability is 0, that no data larger than 45 can occur? No, of course not. Obviously, it could be that these values do exist, but they just haven't been sampled yet. So how do we deal with that? So for this, we need some model that describes the random process by which our observations were generated to say something about the probability of Z being so extreme. So we need to somehow use this mathematical model for extrapolation. So the mathematical model that we use for this is the concept of a random variable. And what is a random variable? Well, if we go to our arching exercise, the random variable is the process by which the imprecision of the arrow flying away here is generated. Yeah. And that random variable has certain realizations, and those are the actual values that occur there. So we have a random variable x, for instance, and we usually use a capital to denote the random variable. It has, we don't know the exact value of that variable because it's generated by some random process. It can have any possible values, for instance, a value x, and we know what the probability is that the random variable is smaller or equal to that particular value, or in between a certain range of that value x. And we can sample the random variable, and then we get our actual observations, and those are samples of that random variable, or often called realizations. Yeah. So we have the random variable, capital X. We have a certain possible value or a range of possible values that value can have, and attached to each of those possible values is a probability. And we can draw actual realizations of that random variable, and those are then our observations. So this is the mathematical model that is underlying the idea of a random variable. So to put it in more official language, a random variable is a variable that can have any set of different values generated by some probabilistic mechanism. In our case, the archer that is a little bit shaky. And before the arrow flies, we do not know the value of the stochastic variable, but we do know, based on experience or reasoning or any other way of deriving it, the probability that a certain value can occur. So that's the definition of a random variable. Now, random variables can be either continuous or discrete. For instance, looking here, we see that this random variable can have any, if this is the wheel of fortune, it can have any value between 0 and 1, any random value. But of course, it can also be infinite between, or continuous between 0 and infinity, or 10 and 20, or minus infinity to plus infinity, depending on the type of real variable we try to describe with our random variable model. It can also be discrete, where we have a countable number of outcomes, and attached to each outcome is a probability. Now, like I said, the probability that a certain value or range of value occurs can be obtained empirically, but often it can also be obtained by construction or by reasoning. For instance, if we think about the throwing of two dice, we can actually imagine, if we throw two dice, what the possible outcomes can be, and they can be ranged between 2 and 12. And we can actually attach a probability to each outcome because we can reason it out. For instance, what's the probability that the outcome is 2? Well, then one die has to have the number of 1 and the other number of 1 as well. So the probability is 1 over 6, and assuming that the outcomes are independent, is 1 over 6 multiplied times 1 over 6 is 1 over 36. If we think what is the outcome, that it can be 3. Well, there's two possibilities that we can have 3, 1 and 2, or 2 and 1. So there's two possibilities when we throw two dice that we end up with a total number of 3. So it's 2 divided by the total number of possibilities, which is 6 times 6 is 36. 4, we can reason the same. We can have 1 and 3, 2 and 2, and 3 and 1, right? And in all these cases, we end up with 4. So there's 3 different possibilities that we have a sum equal to 4. So the probability is 3 over 36. So, and so on. So this gives us the probability distribution of the outcome of throwing two dice. Before we throw it, we do not know what the outcome is. The outcome is the result of a random process, the throwing of two dice. Well, you can maybe reason that it's actually deterministic, but for all reasonable, and that if you know exactly how to the physics by throwing it, you could figure out what it will be. But for all practical purposes, this is random. And so it's a random process. We do not know beforehand what value it will obtain. We do know what values it can take, or what range of values it can take, and we can attach a probability to each of those values. So that is the mathematical model behind the throwing of two dice, and that's called a random variable. Now we can estimate all kinds of measures of a random variable, but we will start by the definition of the expectation of a function. This seems to be abstract, but we come back what this is. So if we have any random variable, in this case a discrete variable, d, which is the outcome of the throwing of two dice, then any function of that random variable, the expected value of that is defined as a function of the possible outcomes times the probability that that outcome occurs. So it's a weighted sum of the function of the outcome multiplied times the probability of the outcome as weight. For instance, if our function is equal to the square root of d, d being a possible outcome of the throwing of two dice, then the expected value of the square root of d is 1.444. That's the square root of 2 times 1 over 36 plus the square root of 3 plus the square root of 4 and so on, all multiplied times their respective probabilities, and we end up with this number here. So that's the expected value of the square root of capital D, when capital D is a random variable modeling the throwing of two dice. Another example, if phi as a function of d is d over 1 plus d, we get a similar series and we compute the expected value as 0.86. Now, of course, the simplest function is simply that phi is equal to d, and then we get the mean, or the mean of the function. So the mean is actually the expected value of d is the sum of the outcome weighted by the probability of that outcome. So the weighted sum of probability weighted sum of the outcomes is the mean of the distribution. And if we do that, we get 2 times 1 over 36, 3 right? 2 over 36 and so on. And if we calculate that, that's 7. And that's actually exactly what we would expect, because there is the mean value, just the middle, in this case, of a symmetrical distribution. So on average, if we throw many dice and we take the average of the sum that we find, we end up at 7. So empirically, we could actually estimate it by doing a lot, n, which could be many trials. Maybe 10,000 times we throw 2 dice, and we compute the mean number of outcomes, and we end up with the expected value, which is going to be very close to 7. Actually, theoretically, if n goes to infinity, it would have to be exactly 7. So that's the expected value of the mean. And that's actually also a measure of the centrality. We already saw that the mean can be, for descriptive statistics, a measure of the center of mass of the distribution. Now the mean computed with the probabilities is also likewise the center of mass of the probability distribution. Now we can also have a measure of spread, which is the variance, which is nothing more than the expected value of the outcome minus the mean squared. So we take the values of the possible outcomes, we subtract the expected value or mean, we square it, we multiply times the probability of that outcome, and we sum. We get a weighted sum, therefore, and that gives us the variance. Yeah, of course, the square root of that is the standard deviation of the random variable. Now we see how it works here. The variance of the random variable that represents the throwing of 2 dice. This is the value, this is the mean. So we subtract from each possible outcome the mean, as you can see, and multiply times its probability. And if we add it up, we end up with this irrational number, which is the variance, and we can of course also get the standard deviation. Likewise, we can also do it empirically. So this is calculated by reasoning and construction, but we can also calculate it empirically by throwing 10,000 times 2 dice, first estimating the average, like we or the mean, like we saw in the previous slide, subtracting that mean from each outcome that resulted from throwing 2 dice, adding those up, and then dividing by the number of trials minus 1. Now this is something different than we showed in descriptive statistics, because now we're estimating the actual value of the mean, but we're estimating it with an estimated value of the variance, and we're estimating it with an estimated value of the mean, not by the true mean. And this will cost us 1 degree of freedom. So to get a statistically unbiased estimate of the variance, we have to divide by n minus 1 instead of n. And n minus 1 is the number of degrees of freedom, and we lost 1 degree of freedom because we're using here the mean instead, that is estimated from the data from the trials, instead of the actual mean of 7. Yeah. So this is just to show you that we can actually reason out from the probability distribution what the mean is, which is and the variance, but we can also basically do the experiment and get an empirical estimate of that true variance. Okay, now let's move to continuous variables. So up to now we've been looking at discrete variables. How does it work with continuous variables? Well, with continuous variables, for instance, this is a continuous variable that is between 0 and infinity, for instance, hydraulic conductivity or concentration, and it can take any value in between. So the probability distribution has a smooth, continuous form. Yeah, we also call that a probability density function. not a probability function, but a probability. The discrete one is called a probability mass function. It's actually nothing more than a histogram. And this is a probability density function in continuous. Now, can we read out a probability from this? Can we get, okay, suppose that we take Z1, what is the probability that Z is equal to Z1? Can we read it from the probability density function? The answer is we cannot. This is wrong. Because this is not, on the axis here, is not an actual probability, but it's a probability density, which is something else. This is the probability per unit mass of Z. It seems a little bit abstract, but we'll come back to that in a few slides to see what I mean by that. What we can do, well, just basically go to, for instance, the room temperature. What is the temperature at an arbitrary point in your room? There's an infinite number of possible values. It's a continuum of temperatures that you can have. So what is the probability that Z is exactly equal to this number here? Well, of course, this can go on, the number of decimals behind can go to infinity. So actually the probability of exactly that number is 0. But we can calculate that what is the probability that it's between 10 and 15 centigrades, for instance. So we can calculate intervals from the density function. Just like in the relative frequency distribution or density distribution directly estimated from the data, and getting the probability that it's between 20 and 30, get that from adding up the areas underneath the histogram values here. We can also compute the area underneath the density function to get the probability that is between Z1 and Z2. Yeah. So how do we calculate the area underneath the function? We take its integral. So we integrate between Z1 and Z2 of the probability density to get the probability. Now we go back to the formal definition of probability density. The formal distribution of probability density is actually that we take the probability between Z and a little part away from Z, so we have a very small interval, and then we divide it by dz. So it's the probability of Z being between Z and Z plus dz. That's the integral of the probability density between Z and Z plus dz. And we divide it by that little interval dz, and then we take dz to 0. Where we have the additional condition that the integral between minus infinity to plus infinity, so that's the area under the total, and the area under the curve has to be equal to 1. So this is the formal definition of a probability density. You can see it's the probability per unit mass of Z. So what we can do is take the integral of what we can do is take another function. It's called the cumulative probability distribution function, which is a little bit which is actually related to the cumulative frequency distribution of the data that we saw before in chapter 2. And from that we can indeed read a probability. So this thing goes between 0 and 1, and this gives me the probability that the random variable Z is smaller than lowercase z, or in this case Z1. Yeah, and that's the cumulative probability distribution function. By the way, if we want to know what the probability that Z is larger than Z, we just take 1 minus the probability that z is smaller equal to z. So that's the way we can get exceedance probabilities. So the cumulative probability distribution function gives me the probability that something is smaller or equal than a given value. And if we want to get the value that it's larger, we have to take 1 minus that value, 1 minus the cumulative, the value read from the cumulative probability distribution to get the exceedance probability. Now, just like we saw that we can get from the cumulative frequency distribution in the histogram, we can get the probability that something is smaller than a certain value. We can get it both ways. We can integrate the probability density function between minus infinity and z, in this case z1, to get the probability that z is smaller than z1, or we can directly derive it from the cumulative probability distribution function. So you can see that the density function and the cumulative probability distribution function are related in that the cumulative probability distribution function is the integral from minus infinity to z of the probability density function. So the other way around, if we want to get the probability density from the cumulative probability distribution, we take the derivative of that thing. So the derivative of the cumulative probability distribution function is the probability density function. Now, we can therefore, if we want to know what is the probability that z is in between z1 and z2, then we just integrate the probability density function between z1 and z2, and we get this area. Or we do the same, we can get the same from the cumulative probability distribution function. If we have that, we take the probability that z is smaller than z2, subtract the probability that z is smaller than z1, and that difference is exactly the area underneath here, and is exactly this probability that z is in between z1 and z2. So two sides of the same coin. Okay. Now, let's do a little exercise just to see what happens here. So suppose this is, so I'm just getting out of the mode. You still see it, I hope. You still see, I'm going out to presentation mode and make a new slide here just to, so the question here is, consider the following probability density function. For instance, this is the probability that the intensity of a certain rainstorm is equal to, basically this is the probability density of rainstorm intensity, for instance, of a 1 hour rainstorm. Derive the cumulative probability distribution, the CPDF, from this one. Now, let's do that. Let's get this done. Get this a little bit up. Hopefully this is going to work. So let's see if this, yeah, if we can make this work. So we have that the cumulative probability distribution is minus infinity to z 1 over 10 e to the power of minus z over 10 dz. So we take the primitive of that. That is minus the e to the power of minus z divided by 10, and then evaluated at minus infinity and z. Now, of course, z is larger than 0, so we're gonna have to evaluate the lowercase is gonna be evaluated between 0 and z. So this ends up being minus e to the power of minus z divided by 10 minus e to the power of 0, and this thing is equal to 1, so this is 1 minus e to the power of minus z over 10. So this is the cumulative probability distribution function. Now, going to the next, the previous slide, we saw that for what is the probability that z lies between 5 and 10? So let's do that. So the probability that z between 5 and 10 oops. Yeah, that is equal to, we saw that from the previous, that's equal to, come up, fz 10 minus fz 5, yeah? So that is 1 minus e to the power of minus 10 over 10 minus 1 minus e to the power of minus 5 over 10. So this 1 cancels, so that is e to the power of minus 0.5 minus e to the power of minus 1. And if we, well, calculate that, then we calculate that. Let's see. Do I know how this works? Oh, it should be minus, sorry. 0.5 minus and then e. No, that's not how it should be. Then it should be this one, yeah. Minus 1 okay, let's do this on my own. Sorry, I'll just do this on my own. Do it easier, we do it in Excel. Is exp 5 0.239. Okay. Yeah. This is how it is. So this is the outcome. This is the probability. So I first calculated the cumulative probability distribution from the probability density, and then I could calculate what the probability is that something is between two values. Okay. Yeah. Let's move on. So we were here. Let's move on to measures of probability distributions. So we saw that we could get the mean or expected value of the outcome of throwing two dice, this a discrete variable, by taking its weighted sum, probability weighted sum. Well, we do the similar thing with a continuous variable, only instead of a sum, we have an integral, and instead of the probability, a histogram, we have the probability density function. Yeah. And again, we can estimate this from the data, obviously, in the same way as discrete. So there's no difference here. Just taking lots of samples and then take the mean of that. Now we can also have the variance. It's a measure of spread. Like I said, for the discrete, that is taking for the discrete. That is taking the probability weighted sum of the square deviations from the mean of the possible outcomes. We do the same, it's continuous, but we take an integral instead of a sum, and we take the probability density as a weight instead of the probability distribution. And we can estimate it again from the data, where n-1 is the degrees of freedom. Okay, and similarly we can compute the skewness as such, and we can also get it from the data. We already saw that. So we can compute, once we have the probability density function, we can also get the skewness coefficient of the probability density distribution, and we can also get the kurtosis and so on. Some rules that are handy to know. The expected value of, if A and B are deterministic constants, yeah, then the expected value of A plus B times Z is the same as A plus B times the expected value of Z. So any deterministic variable can be taken out of the expected value operator. Yeah. When it comes to the variance, any constant inside the variance operator disappears, because when calculating the variance, we're also subtracting the mean. So this is why these two A cancel. And any deterministic prefactor, in this case B, can be placed in front of the variance operator, but then as a square. Yeah. This is valid for Z, both continuous and discrete. So these two calculation rules are handy to know. Now, we talked about probability density functions, and there's many different types of probability density functions, as we will show later. There are exponential, gamma, beta, and so on. But the one that is most well known, obviously, is the normal probability density function, or Gaussian distribution. Yeah. And this is how it's written. And this is what it looks like, right? It's the so-called bell-shaped curve, where this is the so-called, where exactly on the top, it's the mean. The thing, in this case, of a Gaussian function, the thing is that the modus, the value of Z with the largest probability density is at the same location as the mean. and also at the same location as the median, because this is 50% of the probability mass, and on the other side is also 50% of the probability mass. Now you have the so-called standard deviation, and that is one standard deviation removed on both sides. We get 68% of the probability mass, and two standard deviations, actually 1.96 to be exact. We get 95% of the probability mass, and three, it's 99.7% of the probability mass. Now, in the early days, these things were tabulated in tables like this, and we still learn how to use it in this lecture series, because it's basically gives you a lot of insight on how to deal with this probability density function. This is the probability density function of a standard normal distribution. So that is this one, but with a mean equal to 0 and a standard deviation equal to 1. Yeah. So if we want to know what, and often for the standard, for a random variable that obeys the standard Gaussian distribution, this Greek symbol chi is sometimes used. And for instance, if I want to know what is the probability that chi is smaller than equal to 2.13, so this is 2.1, 2.10, 2.11, 2.12, 2.13, so that value is 0.9834. Yeah, that is the way you do it. Yeah. This is how you use this one. Now, of course, these days, all these values are already tabulated in all kinds of programs. For instance, in Excel, you have the function norm.dist, and if you give here the value that you want the probability of, the cumulative probability value of, so the probability that x is smaller than that, z is smaller than that particular value, for a given mean and a given standard deviation, and then if you fill in cumulative, it returns the cumulative probability and not the probability density. This is standard in Excel. Now, it's interesting to look a little bit about the relationship between the normal and the standard normal random variable. The standard normal, like I said, is often denoted by chi, which is a normal distribution with 0 mean and a standard deviation of 1. Yeah? So the mean is 0, the standard deviation is 1. A normal, any normal distributed variable has a Gaussian distribution with a given mean and a given standard deviation, and it can be related to the standard normal by that z is equal to its mean plus its standard deviation multiplied times a standard normal deviate, standard normal distributed random variable. Yeah? So z is mean plus sigma times chi. Now this is handy because then we can actually get, for instance, if you want to know what's the probability that z is smaller or equal to 10, that is nothing more than the probability that the mean of z plus the standard deviation chi is smaller or equal to 10. Then we can rework this guy here, and we get the probability that chi is smaller or equal than 10 minus mean divided by sigma. So we get, and then we can actually, if we calculate, if we know mean and we know sigma, we can calculate this number, and we can look then in this table what the value should be. Of course, in Excel, actually, it's one command. You type in is equal to norm.dist, fill in 10, any mean and standard deviation that you know is true for this particular value z, and true that you use a cumulative probability distribution function, and you get this probability back. In R, you use this function here. Okay. Now let's go to the normal and log normal distribution. Often we have, especially in hydrology, many of the variables are strictly positive. For instance, hydraulic conductivity and concentration always vary between 0 and very large values. And if you take the logarithm of that, they often tend to a Gaussian or normal distribution. So in this case, Z is a log normal distribution, which varies between 0 and infinity. And if we take a logarithm, a natural logarithm of that, that's why we get something that has a normal distribution that varies between minus infinity and plus infinity. And why would you do that? Well, because the properties of the Gaussian distribution are quite handy to work with, to calculate exceedance probabilities and so on. So this is why it's used a lot. These are so-called transformation formulas. You can calculate, if you know what the mean is of the log normal variable and the variance, you can calculate the mean of the log normal and the variation and the variance of the log normal from the mean of the normal one, or vice versa. So if you know what the mean, if you know what the variance and the mean is of the log normal, you can calculate first the variance of the normal distribution and also the associated mean later on. Now this is what we're going to do in the next exercise. So it says hydraulic conductivity for an aquifer has a log normal distribution with mean 10 and variance 200. What is the what is the probability that a non-observed location, so I'm going to a non-observed location in the aquifer, I take a sample, what is the probability that the hydraulic conductivity at that location will be larger than 30 meters per day? Okay, so how is that done? We have the mean of Z is equal to 10 and the variance of Z is equal to 200. Yeah? Now, if we want to do exceedance probability, it would be nice to have a Gaussian variable because that's tabulated and a log normal is a little bit different. So it's easier to first convert it. So I'm going to use the conversion formula. That is on this one. I'm going to copy this one a little bit. See if I can get this thing copied. These two. So put them here. And then hopefully it works again. Yeah. So first I'm going to calculate. So I want to know y is ln z, and I want to first calculate the mean of y and the standard deviation of y, because if I have that, then I can actually say that y is the mean of y plus the standard deviation of y times the standard normal, and I can actually get my probability reading from the table. So first I'm going to do this conversion. So as you can see, this one has the variance of y in it, so I have to start by this guy because that only has the variance of z and the mean of z in it. So what I'm going to do is that the variance of y is equal to ln the mean. The variance is 200. The variance, the mean is 10, but you have to take the mean squared, so that is 100 plus 1. So that's equal to the ln 3. And then the mean of y is equal to ln 10. This is the mean of Z minus ln 3 divided by 2. Yeah, so let's calculate this one for carrying it further. So this is equal to 1.753. So, okay, so now we have the probability that Z is larger than 30 can actually be the same as the probability that ln Z, which is y, yeah, is larger than ln 30, because the logarithm is a transformation that doesn't change the order of the variable. So then, which is actually 1 minus the probability that, move this up, sorry. We're getting there. Oh, I have to. Yeah. That y, because y is equal to ln Z, is smaller equal than ln 30. Yeah. Now this is equal to. Let's get this thing first. So the probability that y is smaller than equal, we can replace y by this guy here. We write the normal distributed variable y, which is ln Z, as a linear combination of the mean of y plus the standard deviation times the standard normal deviate. So that is equal to the probability that the mean of y plus the standard deviation of y times chi, sorry, is smaller equal than ln 30. Yeah? So that gets me the probability of chi is smaller equal than ln 30 minus the mean. What's the mean of y? We had that. That is 1.753 divided by the sigma. Well, the variance is ln 3, so that's the square root of ln 3. So, new slide here. So we want the probability then ln 30 minus, what was it again? 1.753 divided by the square root of ln 3 is the probability that chi is smaller equal. Now let's get this thing calculated in the calculator. 1.753 0.572. So that is, and then we go back to the table, 1.752, 1.75, say, 1.7, 5, oops, 0.599. So the probability that y is larger than ln 30 would then be equal to 1 minus 0.9599 is 0.041. Okay? So you see what we've done now is we calculated, we use two things. We use this transformation formula to get the mean and the variance of a Gaussian distribution. And then once we had that, we could use the properties, the relation between the standard normal distribution and the Gaussian any Gaussian distributed variable to calculate the probability that something is smaller or equal to a certain value for a standard Gaussian variable. And then we also make use of this property that 1 minus the probability that the probability something is larger is equal to 1 minus the probability that it's smaller or equal. So we do use three different properties of a random variable to calculate in the end the exceedance probability for being that hydraulic conductivity is larger than 30 meters per day. So it seems like a lot of work, and it is, but if you compare it to the silly thing is obviously if you put this into R, it's basically one line of code, and you get the same you get the same answer. Of course, you don't get the insight. All right. Okay, let's move on. This is actually the last slide for today. You can see here we already saw the normal distribution and the log normal distribution and how they are related. But these are other distributions that can be used. Like I said, the normal distribution would be something that you would typically use for symmetrical variables like groundwater levels, for instance. They can be both positive or negative with respect to a certain reference level. Log normal, think about concentrations, hydraulic conductivity that are typically log normal distributed. Then this is the gamma distribution. Often rainfall intensities for a certain duration of rainfall is gamma distributed, and if the duration is very small, like a 1 minute rainfall or a 1 hour rainfall, a special form of the gamma distribution is the negative exponential distribution. It's just the same type of distribution, but a special case of that is often used for rainfall intensities. Then the beta distribution, you can see that this would be very well suited for instance, porosity that or soil saturation that will change between 0 and 1. And then this is the Gumbel distribution that will be viewed a lot in chapter 4. This is a distribution that is very well suited to describe extreme values of a certain phenomena. For instance, extreme runoff or extremely high groundwater levels, for instance. And then finally, this is the Weibull distribution that is often used to model minimum values or also rainfall intensities.